Hi, this is Tim Rohwer from Rohwer Music Studios, and today we're going to be talking about how we measure pitches in terms of both frequency and letter names. The first thing that I wanted to go over is that each pitch has a frequency, and that frequency is measured in hertz, which is how many times per second or how frequently per second each wave occurs. If you have an object and it's vibrating back and forth at 200 times per second, then the frequency of that object will be 200 hertz. Likewise, if something is vibrating at 400 times per second, that frequency will be 400 hertz. Now, what this means for the actual pitch that we hear is that the slower something is vibrating, the lower the hertz, the lower the pitch will be. The faster that something is vibrating, the more frequently is vibrating, and therefore the higher the hertz, the higher the pitch will be. In Western culture, we're used to hearing a few distinct distances between pitches, and we refer to these with letter names, and this system is a great way to help us visualize these pitch differences. But the actual frequencies of these pitches are measured based on ratios compared to one another. To see this, I've got a chart I want to show you. So this is a chart that shows our distinct pitches and their frequencies, and as you can see, it's not just a straight line up, but it actually has a curve to it. Now this is because as we go from one lower letter pitch to a higher, that would be like a C to a higher C, which we refer to as an octave, the frequency is double that of the previous octave, and so this ratio actually creates an exponential kind of a function. If we zoom in on our chart here, then we can see this just a little bit more closely. So our first pitch on this chart is C0, which is a C in the lowest octave. Its frequency is 16.35 hertz. And then we have this pitch, which is C1, which would be an octave above the C0. And the frequency for this is 32.7 hertz, which is actually double that of C0. Now the difference here isn't too pronounced, but it actually gets bigger the higher up in frequency that we go. So if we go to another spot in our chart, we have A4, also referred to as A440 since the frequency is 440 hertz. The A an octave higher, A5, would be 880 hertz. And so that doubling each time that we go an octave creates this kind of a exponential growth rate in our frequencies. So in between each octave, we actually have smaller distances as well. In particular, we have a series of whole steps and half steps that make up our octave. And for these smaller distances, we use specific ratios to allow us to have our notes in between equally spaced apart. Now at this point I do need to point out that we're currently referring to equal temperament, which is a system of intonation that's used for instruments that you can't easily adjust your pitch, such as a piano, organ, guitar, and a few others. However, there are other tuning systems out there. One of these is called just intonation, which uses whole number ratios in determining distances between pitches. And in this system, the half steps and whole steps can actually be slightly bigger or slightly smaller in different circumstances. There's a great advantage to this, though, in that the pitches will actually resonate better, since the waves that are being emitted from the instruments will be strengthening each other when they line up. And there's actually quite a lot of beautiful sounds that happen when you have this just intonation. And those amazingly beautiful sounds really can only happen when you have these pitches that are lining up perfectly. Once again, though, there are instruments that you can't adjust mid-performance, and for those instruments, we use a system that's called equal temperament. And for this, the frequencies and the wavelengths of the pitches, they don't line up as much as in just intonation, but the advantage is that you can actually play in any key, and the half steps and the whole steps will sound more in tune overall as a whole than they would if you were trying to change keys mid-performance. So there's some math that we use to determine these equally distant pitches, and what you do to determine that is you take the 12th root of 2, and this will actually give you the ratio that you need to make all of the pitches the same ratio from one octave to the next, because if you take this 12th root of 2 to the 12th power, then you get just the number 2. And those 12th root as well as to the 12th power, they both just cancel each other out. And with this figure, the ratio that you end up getting is about 1.06, a little bit less than 1.06. In order to visualize this a little bit better, we're going to take a small cross-section of our graph here. And what I'd like you to be able to see is how our frequencies line up with our pitches. To do this, I've taken our chart and I've actually colored it in so that you can see the changes between the individual pitches. I've also made it so that pitches that are the same letter but are just in a different octave have the same color. And in our first example, we have a pitch that is slowly shifting between all of these frequencies. As you could see as we moved along that graph, the wavelength was slowly changing with the pitch. However, it was moving more rapidly. Let's see the same thing again now, but this time hearing the distinct pitches. To me, when I hear these small pitch changes, it sounds more like a linear progression, just kind of slowly moving up. And really, that's one of the great advantages of using these pitch names. It can help us visualize these differences between these pitches and understand their relationships better. So what we're going to do is we're going to simplify our measuring system, these frequencies, and we're actually just going to kind of flatten it out so that it's more of a ruler rather than a curve. Up to this point, I would say that everything that we've done so far, as far as measuring these distances, has been pretty straightforward. However, there is something that's a little bit unique to this system of measurement, which is actually based on what we refer to as the major scale, the most commonly used scale in Western music. The pattern for this major scale is whole, whole, half, whole, 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 half. Because this is the most commonly used pattern, what we do is we adjust our ruler and we actually make it so that instead of each letter progressing equally distant from another one, we have a couple places where our letter name pitches are closer together. And what this ends up doing for us is it allows us, as we progress through this musical alphabet, these letters, that we keep our major scale pattern of whole, whole, half, whole, 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 half. Now, there are some times in which to keep our major scale pattern, what we do is we utilize some of these pitches that are in between, some of these other half steps. And in some instances, we raise some pitches, and in some instances, we lower some pitches to help us keep the overall pattern of our major scale. But when we don't have any adjustments to keep us in that major scale pattern, the note we actually start on to get this major scale pattern is the note of a C. And because of this, C ends up being sort of our musical center. Now, this actually brings up an important question, which is why C? Why is C our musical center? The biggest reason for this is that the letter name system that was created for music was created so long ago that the meanings of our scales and what was most popular has actually changed. So when this letter name system was being created, more than likely the most popular scales were not major scales. In fact, they were likely minor scales. And the minor scale that doesn't need any adjustments, raising pitches or lowering pitches, is actually A minor. And slowly over time, people's preferences changed so that they started to like songs that use this major scale more. So with our pitches in their natural or unchanged position, what we get is half steps between the notes of E and F and B and C. Now, musicians and composers, what they might want to do is take this set of notes and very subtly adjust the feelings that they get from this. And to do that, they might alter this major scale and take some of the notes and raise them, or take some of the notes and lower them. And what we do to indicate a movement from the natural pitches is that we either put a sharp or a flat that shows for sharps to move up a half step on our ruler, or for a flat to move down a half step on our ruler. One of the instruments that's easiest to see these natural pitches as well as these adjustments, the sharps and flats to these pitches, is the piano. And that's because the keys on these keyboard instruments were actually laid out to help you visualize both the natural pitches and movements away from these natural pitches. However, for a lot of musical instruments, it's not quite as easy to see this pattern of notes. Let's take as an example a trumpet. So a trumpet has different valves that when you depress them, it changes a length of tubing that allows air through the trumpet. then depending on a number of factors, such as how you shape your mouth and how fast the air is moving through the trumpet, as well as several other factors, you get different pitches. And one of the things that you might think with the trumpet is that I just blow air into it and I push down these different buttons which give me different notes, which is not the case actually. And not only that, but the depressing of these different valves is not sequential. So if I want to move a half step down, I press down the second valve. If I want to move a whole step down, I press the first valve. If I want to move a whole and a half step down, then I press the first and the second valve. And there are lots of different combinations of valves that give you different pitches. Another example would be the string instruments, which when you have a string instrument, you have the string, and if you put your finger down on the string, it tightens that string up by a certain amount, and that gives you a different pitch. And for each of these different pitches, you don't just set your finger down equally distance apart. And depending on the string instrument, this leads to a lot of combination of different possible fingering patterns. And frequently you'll have some fingers closer together to give you that half step, and sometimes you'll have fingers further apart. And one of the things that makes string instruments even trickier is that not only do you have these large variety of possible finger patterns, but because where you place your fingers on the strings to get different pitches is also based on ratios, then where you place your fingers changes depending on where you are on the string. So there are places where half steps actually look quite smaller and places where half steps actually look quite bigger. Now, every instrument is going to be slightly different, and how you change the pitch on those instruments varies from instrument to instrument. But I hope you have a better understanding of how we measure those different pitches. That's all the time we have for today's video. If you have any suggestions for future topics on music theory that you'd like to learn, please leave a comment below. If you found the video helpful, make sure and give it a thumbs up so that other people can find it more easily. And if you want to stay up to date on what's happening on the Rohwer Music Studios channel, then go ahead and hit the subscribe button as well.